Our speaker today is Hans-Peter Grassel, and he's a software engineer and a technical trainer at Net Economy. And he's here to give a talk on streaming data on the shoulder of giants. A fun fact about him, he actually wrote the Kafka connector himself that we are using and gave it to MongoDB for us to build upon it. So the talk today is by the expert himself. A few housekeeping things before I hand over the mic to him. Please be respectful of any Q&A that happens at the end of the session so that people can ask their questions in silence. You'll have enough time to go to the next session. We'll be sure of that. And Hans has put in enough effort in this talk, so he would love to get some feedback from you at the end of it. And over to you.
Thank you. Well, good afternoon, everyone. Glad that so many came right after lunch to my session, which is about streaming data on the shoulders of giants. And I think it's not a secret anymore that these two giants that we are going to talk about the next 45 minutes or so are MongoDB, of course, and Apache Kafka. So let me gently dive into this topic with some sort of a business view on the topic before we really get to the technical things. So we've heard that today many times already, that it's very important for companies these days to be competitive on the market, and for that they need two characteristics, namely speed and agility. We know that basically every company, no matter which industry and which size, needs to innovate at ever shorter cycles. We want to basically need fast answers. We need to come up with new ideas at a breakneck pace. And it sounds very straightforward. Like, everyone needs to manage, process, and analyze data. And so all of us are using data in one way or another. And we do that so that we try to find and unlock some insights which is hidden in large amounts of data typically these days. We don't do that for the sake of its own. We of course want to drive value, we want to make money out of it. Now, this sounds pretty straightforward again, but there is, let's say, a somewhat hidden challenge to this, in the sense that there is this notion of the diminishing value of data. Some of you may have heard about it, so there's different perspectives. You can look at this phenomenon if you want, but this goes back to a research study from Forrester. And the idea there is that if we take a look at basically the age of the data that we have, ranging from sub-seconds all the way up to several months, and we contrast that to the value that this data can have for the business, for decision making, then we see that the relationship is one in which the value decreases very rapidly as the age of data increases. So most analytics, what's termed also as traditional business intelligence on this illustration here, is happening towards the long tail. So at your very far right, you see something that is called the category of historical data, if you want, so things that are hours, days, or months old, or maybe even older. Now, at the same time, we see that the value that this data has is relatively low. And streaming technologies, no matter which of them we concretely use, can help us to push towards the left and come up with much faster insights that we would need for actually time-critical decisions for our business. Now, when we take a look again at what historic ETL, at least technology-wise, was all about and still is today to some degree, we see that this can be rather painful to achieve this transition towards this left side of the distribution we saw just on the previous slide. So a lot of these technologies are batch-driven, inherently batch-driven, and this means that so we definitely get slower answers than we would like to, and it can also be brittle, or at least susceptible to error to some degree. Now, when we use a batch-driven system, we need to be aware of the fact that this is actually an anti-pattern for speed and agility. So in fact, it's something like that you would build in latency by design into your solution when you go for a heavily batch-driven approach, or at least a batch-first approach, if you want. Now, to alleviate some of the pain that comes with that, we can use streaming technologies. And we will hear today that we can combine, so MongoDB as the operational data store, combine it with a streaming platform, event streaming platform like Kafka, in order to achieve much lower latencies for anything that we would like to know about our data. Like you can see that streaming technology is, in that terms, an enabler for speed and agility. Now, there are many different ways to look at modern or more modern data platforms. And I mean, we've heard it in the keynote this morning, what the MongoDB side of things means for a modern data platform. I try to do that and show you this at one abstraction level higher, in the sense that we have something that is called a streaming data fabric on this slide here. And the specifics for now don't matter. But the idea is that you have some sort of streaming kind of technology in place that allows you to nicely decouple any data flows that you might have inside your whole company. Now you can have several different apps that connect to this streaming fabric. They push data into the fabric, and then other connected applications can leverage the data either in a one-to-one fashion, like simple pass-through scenarios, or you do something in between. Now, we cannot only integrate through this fabric on an application layer, but we can even do that one level lower than that, namely on the persistence layer itself, where we can then say, well, it's not so much, maybe your problem is not so much about connecting applications or services, but you want to integrate originally disparate data sources with syncs across your whole landscape. And you can do that as well. And then to complete the picture, there is oftentimes the need for leveraging any kind of streaming technology that allows you to do things to the data that flows through the fabric basically in flight. So as new data passes by, you do some things like filtering, transformations, enrichments, like joining things together, or pre-aggregations. We have heard in one of the earlier talks today, like an IoT scenario, that pre-aggregation can be a very good idea when you have to deal with high velocity and streams of data and simply large amounts of data. We can build such a fabric on the shoulders of giants. On the one hand, again, we can leverage MongoDB as the operational data store. On the other hand, we can make use of the de facto standard for event streaming platforms, which is Apache Kafka today. Now, being at the first-class MongoDB event, I think it doesn't it's not necessary to highlight all the different aspects why it makes sense to use a modern database for like MongoDB for such scenarios. But I think it boils down to primarily two things. First and foremost, of course, the richness and flexibility of the document model itself, and the fact that MongoDB, as we have already heard today many times as well, can be run anywhere. Like we can use it to run clusters in the cloud, public cloud, or in your own data centers, whatever that is, to scale for your workloads accordingly. And we can not only scale that thing, but we can do that in a resilient and highly fault-tolerant way. Now, switching the discussion over to Apache Kafka, let's see what follows as some kind of minimum viable introduction. But first, a quick raise of hands. Who has heard about Kafka before? Oh, that's almost everyone, which is great. Who has not only heard about it, but tried it, or is even using it? Oh, that's almost half of you who at least know about it. So then I'm going quick here. So whenever you dive into the world of Kafka, you will be immediately confronted with the fact that it is a so-called streaming platform. At the same time, you might wonder what that even means. First, some just characteristics which are very similar to MongoDB on a high level, in the sense that these are characteristics that are fundamental and that we actually expect from any modern data processing system. Like again, Kafka is not meant to run on a single machine, even if I'm going to do that later on my machine for the demo. You run it across many machines. You do that by running typically many of so-called Kafka brokers across these machines and get horizontal scalability for your workloads. And you can very specifically tweak and tune Kafka when it comes to like delivery guarantees of messages, when it comes to the storage, like retention times, how long do you want to keep the data there, and you can even tweak and tune like its replication behavior, which in turn will give you fault tolerance and high availability. Still, you have no idea maybe what is meant by the term streaming platform. And in order to find out, let's take one step back and ask the question, what is stream processing anyway? What is this about? Or sometimes it's just called streaming for short. And there are plenty of definitions out there in the wild, but one which I particularly like is given by a guy called Tyler Akitau, and he describes it in very simple terms, actually. He says that stream processing is a type of data processing that is designed with infinite data sets in mind. And this is rather generic, I'm aware of that, but I think it still captures the essence of what streaming is about rather nicely, namely that you are able to deal with unbounded data sets. So you cannot just like write a query and eventually the query will have seen all your data and come up with an answer, but you have to be able to process data continuously as new data happens and arrives. Now, stream processing can be found basically in every company in various different ways. Like anything can be interpreted semantically as a stream of events, not only technical things like API requests or some things like that, but also, more importantly, like business actions that happen in your systems, like a stream of user registrations or a stream of order placements in an e-commerce solution, or a click stream, like coming from users clicking around on websites, or a stream of search requests. Anything is a valid way to try and understand and model it as a stream of events. Now, every time we engineers have to deal with high-velocity unbounded streams, we need special technologies, purpose-built systems that allow us to deal with this unboundedness of event streams. And I think like users are impatient, we heard that as well, they are demanding, like everyone wants everything right here, right now, and this is especially the fact where I think that Kafka together with MongoDB can give us a very high user satisfaction in that regard. So talking about Kafka very quickly, I want to walk you through, for most of you, it should be some kind of repetition, but very briefly, I want to walk you through the main touch points. What do we actually use as developers when we build solutions on top of Kafka? So it's a quick tour through the API. So first of all, like applications can leverage on a very low level something called the producer API. We can just use it to write from your favorite language, like there's drivers for basically all popular languages, and send our data and have it stored in Kafka topics. Like Kafka itself doesn't care about message structure, so at the end of the day what it does is it stores sequences of bytes. Then the consumption side of things, where we use the consumer API, we want to do something with the data that like resides or actually arrives in Kafka topics, and we want to do that again with the consumer API. We have a lot of freedom how we actually process and consume this data from topics. We can not only read messages once, but we can expose the same messages to many applications that might be interested in this data, and even the same application can read data more than once, so we can, for example, go back in time and replay messages from the past if we would need that. Now this is again the application layer and the area that you would use when you have very specific needs that require this, in that terms, low-level interaction with Kafka. Now, I also talked about integrating data stores earlier, and this is where the Kafka Connect API comes into play. Like this happens typically on the persistence level, like you integrate source databases with sync databases on the other end. And this is not only an API, this is a framework that can be used by people that want to implement so-called connectors that do the job of either bringing data into Kafka or moving data out of Kafka towards your sinks. Then the stream processing part that we will also see in the demo afterwards is used like to do something with the messages in flight. Like it doesn't really matter what the origin of messages is, can be coming from the Connect API, can be coming from the Producer API, no matter where it comes from. You can filter, you can enrich, you can transform your data, and you can do like aggregations on the fly. This is for developers, like there's Java and Scala API bindings for that, and especially for that reason, they're like to include also like non-developer folks into the stream processing part, we can use something called KSQL there. It's just an abstraction layer on top of the KStreams API, which is very handy in the sense that it allows us to declaratively explain or describe our stream processing needs, and then we ship that basically SQL-like file to a so-called KSQL server, and it does all the heavy lifting under the covers and starts to happily process the data. So this completes basically the picture of the most important APIs and touch points that you have with Kafka. So in a nutshell, again, these are the APIs, but I want to leave aside the rest and just focus for now on the Connect API, which is about these streaming data integration scenarios. We want to build pipelines and connect source systems with sync systems. So a bit more about Kafka Connect. Again, the basics. So the idea is that you can connect any source with any sink. By putting Kafka in between, you nicely decouple the data flow between these two systems. So, for example, your sink can be down for some time. The source is not affected. It happily pushes data to Kafka, and when the sink comes back online, it continues basically where it left off. So ideally you don't even realize that, or at least the source in that sense doesn't even realize that the sink was away for some time. And when I say any, it can be literally any. Like you decide as an implementer of a connector what you want to integrate with. It can be as simple as a file system where you watch a folder which receives new files, and you bring this data, like maybe it's CSV files resulting from some exports, and you bring this data into Kafka with a connector. Maybe it's a data store, like maybe you want to bring some data from a traditional kind of database to Kafka and do something with the data. Maybe it's REST endpoints that you want to push some data to. Maybe you have services, web services that you want to feed with some of the data that is written to Kafka. Now, all of that can be done if there are readily available connectors for the actual system that you want to integrate with, just by means of configuration. So there is literally no code that developers need to write for that, no plumbing, no nothing. All you do is you configure it properly, which at the end of the day is a JSON configuration file that you publish to the Kafka Connect process, and everything else is done and taken care of by the system then. Now, like I said, often it's about data stores. Source databases and sync databases is what you want to leverage. And to make that a bit more concrete, like there are just a few popular ones up on the slide. So this is by no means an exhaustive list, but at least there should be something that you can relate to on this slide already. There are plenty of more, like you can find them on Confluent Hub, which Confluent being the commercial like vendor behind Apache Kafka. And they are maintaining a curated list of popular connectors, and some of them are open source, some of them are certified, some of them are from the vendor themselves, and so on and so forth. So you can really find a lot of systems to integrate with just by looking at their page. In case you haven't spotted it, yes, there are, of course, connectors available for MongoDB as well. Again, different ones, like the ones that we find on GitHub in the wild, like maybe baked by a single person. And also, we come to that later anyway, there are some official ones for which you can get support. Now, again, a few more details how connectors operate under the covers. So to give you an idea, especially also in context of MongoDB, what that means and how a connector does its job. So starting with the source side of Kafka Connect, we have MongoDB on the left. Now, the responsibility of such a source connector is to try to find ways to get any changes that are happening in the database and read them out of it, create an internal data structure called a source record. Now, once we have source records, these records can undergo an optional kind of pipeline, which are called single message transforms. And as the name implies, we can use these transformations to do basic in-flight manipulations, like Examples for that would be you want to rename a field, you want to blacklist or whitelist certain fields of your payload, in that sense, a MongoDB document. Maybe you want to mask sensitive data like credit card numbers, social security numbers, that should not make its way into Kafka into the first place for legal reasons, for example. And there are plenty of more different single message transforms that you can use. The important part being here that these SMTs are very handy in the sense that they are agnostic to the specific source connector implementation. They can be leveraged on framework level. So all single message transforms that are there work with every connector that is out there. Of course, if something is not supported that you would need, you can write your own custom single message transformations, or you could try to do something very specific and custom in the connector itself, of course. And then afterwards, it's the job of so-called converters, and the most used ones are just there to be used. So actually, you don't even need to care, but the converter does the job of bringing like the message structure into some binary form, so a byte sequence that can be written to Kafka. Now, from the sync side of things, the data flow is actually just reversed. So it first starts by reading byte sequences out of Kafka topics. We have converters for that deserialize the data, like a JSON deserializer or a string deserializer or an Avro deserializer. These are the most popular ones, and then there are also things like, or it's also support, community support, third-party support, like for things like protobuf. Others can be written on demand on your own, of course. And then again, after the conversion, we get an connect internal data representation. Then we can again employ, if we want, single message transformations before the actual records are really handed to the sync connector itself, whose job it then is to safely write the data it receives to the target data store, MongoDB in that sense, natively. So it will create documents that get written to collections at the end of the day, and it will do that message by message in a streaming fashion. Now, I briefly talked about it before. Let's say the problem for companies to adopt this Kafka Connect framework, especially in combination with MongoDB, was that while there were like a handful of connectors out there in the wild, there was nothing really officially supported. Like you know that, like for some people this means it's a side project, or for some it's not even a side project. Some just put up some code on GitHub, and that's it. Sometimes there was no documentation. Sometimes there is, of course, no such thing as a support. So anything that you would miss as a company to have a good feeling and use something like that in production. Now, at long last, the wait was over earlier this year in June at MongoDB World in New York City. The official MongoDB connector for Apache Kafka was announced. It supports both, of course, a sync and a source. The sync is actually leveraging to a very large degree the code base that I wrote myself. Like I started the sync connector implementation in the community 2.5 years ago. So I'm really happy that I could work together with the product team and also with the engineers to basically move that and bring it into the official connector. Like, it's developed open source, so you can find the official connector as well on GitHub, so pull requests are welcome anytime. There's a separate Jira project at MongoDB site where you can file tickets, where you can discuss things. You get official support by MongoDB, of course, and also this should give you some good kind of feeling. From the very beginning, the connector was verified gold certified by Confluent. This is, if you want, a quality label which assures that the actual implementation is meeting certain standards and follows some best practices when it comes to integrating with the Kafka Connect framework. So you can build it from the sources to get the latest snapshot, basically, but more conveniently, you can go, like I said earlier, to Confluent Hub and download the latest release as a pre-built package to use in your project. Now, before going to the demo part, and I think I'm quite good in time still, just 3 very simple use cases that should give you an impression and at least the first idea how you can leverage now this MongoDB connector for Kafka in projects. 3 use cases that I want to share with you. One is building a single customer view, in this example in the field of e-commerce, where online retailers, for instance, they might have like a heterogeneous landscape in place, like most companies don't start from on the greenfield. Like you have maybe several subsystems that you need to address when it comes to building this customer view. You can then use source connectors for these systems and feed all the data that is already there to Kafka, and then of course start to feed also any changes that may still happen to these systems in near real time into Kafka. So it's not something like a one-time migration where you then would shut down certain systems. This is not very practical, also not very realistic. So you want to maybe need to maintain all of these systems for quite some time. So this is how you integrate then after the initial snapshot that you bring to Kafka in, and also react to any further changes that may happen. Now, once the data is there, you can then just configure the sync connector to your specific needs, like basically say, or also doing the routing, like saying which of the topics in Kafka should go to which MongoDB collection. And there, once the data is there, you can then find a way to build your single source of truth for like your golden customer record, your customer 360, however you want to call it. And based on that, you can then drive new applications, which hopefully allow you to do much more than what you could originally do with all the, like, let's say, isolated parts which were referring to one and the same customer. The second use case is about data synchronization in a service landscape. Feel free to call them microservices if you want. Like when we are in a microservice architecture, the recommendation is that when you have many services, each of these services typically has its own isolated database. So it's actually an anti-pattern to share a huge central kind of global database and feed 20 services. That is something that you normally don't do. Now, still, this isolation is nice on paper, but we all know that certain parts of the changes that are happening in one service needs to be communicated to other services. Now, you could do that, of course, in various different ways. Like you could actively inform service 1 that in service 5 something of interest changed. You might start doing it like with maybe even with point-to-point synchronous connections. This works fine as long as you want to share data between 1, 2, 3 services. But this gets quickly out of hand when you have to communicate like a lot of different things from sources to sinks. And this is again where Kafka comes in as a decoupling kind of element, where instead of writing to the database of the service itself, every service writes first all the changes to Kafka topics. And from there, we then configure several sync connectors, which then take the messages that get written to the topic by the services, then route them appropriately and make sure that they land and find their way into the corresponding MongoDB target database instance. And the final use case is here something like a recommendation engine that you could build for an opinion mining kind of use case. And there we try to see that also the other way around could make a lot of sense. Like the first 2 scenarios were about using the sync connector to bring data from Kafka to Mongo. Here we go the other way around. Like we have some user-generated data in terms of surveys and polls, and we want to or we feed that directly into MongoDB. Now we might have the need that some applications that are either already there or that just for whatever reason can't directly integrate with MongoDB want to use that data with very low latencies after it was generated. Again, we can here then leverage MongoDB source connector, which basically subscribes to the change streams feature of MongoDB, reacts to any changes happening in the database. We can do that in a very fine-grained way, like only like listening for insertions to a certain collection, or maybe we want to go all in and say, I don't care, anything that happens in this specific database should be written to Kafka topics. And once the data is there, like anything else can then integrate with this data, like for example, a user recommendation engine which might be written with Kafka streams. And the nice effect again is that there is no need to write any integration code. You just configure to make sure that changes happening in MongoDB will find its way into Kafka so that other applications can use it. Yeah, with that, I want to switch to the demo scenario that I prepared, and let's see some of this in action. So quickly to explain to you what we're going to see, we have a demo scenario that looks as follows. We have Apache Kafka. We have some data generation application. That the actual example is in the IoT domain, if you want, and instead of real devices, which would be a little bit difficult to do here in such a short time span, I have an application which just fakes and simulates two different devices. And these devices use the producer API in that sense to feed data into Kafka. On the other hand, we have maybe an application that is already there, which allows us to manage devices. First, before that part, just a note that I integrated a stream processing application. The specifics don't matter, it's just there so that we see that we do not only do a one-to-one message pass through, but we do something useful like calculating pre-aggregations, splitting a unified stream into two substreams and stuff like that, so that it's a little bit more interesting from an integration perspective with MongoDB. Yeah, then the right side, we have two features that we want to have. We want one application that does some kind of real-time charting. It's again, this is a custom application. We pretend that you write that application on your own, and you want to get a near real-time feed of anything that updates in the stream processor and inside the Kafka topics, and the application gets pushed down servers and events with any changes that are happening. The way this works is that we use the reactive driver here to subscribe to the change streams of MongoDB and then push it down to clients like a browser dashboard over servers and events. And then we have a separate like use case where we say we want to be able to manage devices, the faked ones that are generating the data here on the left side. And device management is also reduced to the bare minimum just for the demonstration. We will be able to deactivate or activate any device, which basically means when we deactivate a device, it should notify the stream processor that the device has been deactivated, and the stream processor should stop processing new data that comes from this device and not produce any downstream data after this deactivation. Now, we have these two worlds which are not connected, and I hope by now you know that it's probably not the best way to try and think of writing integration code on your own to connect both worlds. But you use, of course, the sync connector to bring data over to Mongo and the source connector to react to these device management changes that will, for example, change just a flag, an active flag in the MongoDB document that represents one of the devices. So let me switch out of the slides, enough talking. I want to show that to you. So what's already running on my machine, like I said, is a single node local Kafka deployment. So I just started up everything there is on my local machine to Kafka, and I have MongoDB running on Atlas here. It's a free cluster, so the most primitive thing that you could think of here. Both systems are running, so we use a database on Atlas for that, and we use Kafka, like I said, for simplicity reasons on my local machine. It just gives me a better feeling that if something runs within this room. An honest bare metal deployment, if you want. So if we take a look, we have nothing, like we have a database on Atlas, which just has some metadata for 2 different devices. So we will later see that this true flag will be then changed by the device management application. It becomes false, and this will then be picked up. But first things first, we need some data. So first of all, I'm running a data ingestion process here. So this brings just up a simple Spring application. The specifics don't matter. It just generates some data, but it generates real-world data in the sense that it reads data from an archived real-world IoT use case. So it's about electricity-related data that we are talking here and energy-related data coming from private households. Then I said to have some more kind of visualization options. We run a stream processor. The specifics don't really matter. And after that, we shouldn't see anything, right? This happens on the Kafka side, so there's nothing new so far. But after bringing up the stream processor, I want to run the first connector. So the first connector is run and just basically does a one-to-one pass-through of events and writes it into corresponding collections in the Atlas database. So I show you first what it does, and then I show you the configuration for that. So now if we refresh, we should see 2 new collections. One is called electricity, and one is called heating. And if we take a look, we see we have already 103 documents currently, and this is how the documents actually look like. So I'm going to switch over here. So you see this is some kind of IoT-related data, in this case reflecting the energy consumption in kilowatt hours of a private household. We have the other parts of the data is dealing with heating and temperature-related things. So we split them into 2 separate collections. And like you see, when I refresh here, the document count here is continuously rising. This is because of course, the sync connector does its job behind the scenes, and as new data arrives in Kafka, we see that the number of documents is increasing automatically. So, like I said, I will show you the configuration for that, and it's very, very easy. Like, all it is basically this fragment of JSON configuration that you would send to the distributed Kafka Connect process. What we basically say is we want to read data from these 2 topics here, IoT heating and IoT electricity. We specify the actual connector implementation. In that sense, it's the official MongoDB sync connector here by pointing to it using the fully qualified class name. Then we say, so Kafka records are basically pairs of keys and values, and then and both can have different like structure. For that reason, we can say that the keys should be converted just with the string converter, and the actual payload, the value, should be converted with a JSON converter. Like, none of these are using schemas, that's why it says schemas are false. Then you have the connection URI, which I just anonymized here. And then you say, what is the target database? And that's basically it. You also see one such single message transformation I was using or referring to on the slides. And it is just doing one thing here. It takes from the payload a field called serial number, and it promotes it to become the key. The reason we do that is that we get from a representation where the key, let's say, was just this device ID, and we get a JSON document which then looks like that after the connector has done its work. Using that, we make sure that also the key itself is basically a fully fledged MongoDB document, and this is what will be used as the underscore ID field in the MongoDB document itself. So as simple as that, just by publishing that, the data starts flowing, and you don't need to do anything else. Now, another thing, like bringing up a total aggregation, it's just another connect configuration, and this allows us to just count or get a total counter updated by on the fly, the stream processor counts how many events were seen for each type of data and each device. And by doing that, we should get another collection here, which is just called IoT events count. Like, naming things is hard, I know, sorry about that. So, and this is how it looks like. So we have 2 devices, and each device has 2 different types of payloads it sends. Remember, the heating, one is represents the heating data, and one the electricity data. And again here, if we refresh that, we see that the event counts here are updated on the fly. Like, we see that every time we receive such a payload type for this specific device, the counters go up. Like, total counting is what you can do there again. And nothing here is calculated inside the database itself, right? The database just happily stores that and is able to serve that very, very fastly to any of your clients. And the final thing is windowed aggregation. This is especially interesting for IoT scenarios, because there it makes a lot of sense to let's say employ this notion of pre-aggregation again, such that the database doesn't have to calculate all of this by running CPU-intensive aggregation queries. You see that you can do like different roll-ups of your data. Like, we get 3 more collections here. Like, we get 10-minute, hourly, and daily roll-ups of the power consumption of each device. And if we take a look at the hourly consumption here, we see that we get basically for different windows of the day. Like, let's take this one, which starts at this. Like I said, this is archived data. That's why you see data from last summer. So let's say on this day, between 7 in the morning and 8 in the morning, we received 42 events, totaling 0.53 kilowatt hours in this 10-minute period of the day. And again, all of this is updated on the fly. Like, if we would look for the daily rates, we should see that the current day is still active. So if I refresh here, we see that the counters update in place for the specific device and the specific day. So we are on the 2nd day here, and you see that the energy consumption still counts up because the day is not over. So again, you get basically as a byproduct of the stream processor, and by leveraging the sync connector, you get this data directly into MongoDB. And finally, and then I'm already done, I said I bring up this real-time view, a very simple application, and I also set up the other connector, like the source connector, which will listen for changes in the device management collection of MongoDB. So I get over to first of all, to the dashboard that gets fed by MongoDB change streams. Looks as follows. Like, we see first device, second device. This is just the total event count, and down there we see the hourly aggregates, and you see as new data arrives, the bar charts, if you want, are updating again in near real time. So this is really live dashboards that we are talking about, in the sense that it's not something that refreshes like in pre-defined intervals, but this is something where we push data coming from Kafka to Mongo over change streams and servers and events down into this very, very simplistic JavaScript application here. So with that, I actually want to just show you that we can deactivate the devices, and shortly afterwards, we should stop receiving new events. It's already happened. Now everything comes to a halt, right? The chart stops, and no new data, because this deactivation signal was sent with the source connector to Kafka, and the stream processor got notified that it should stop processing data for these devices. And that's why we don't see any updates. If I activate it again, like very soon, the data starts flowing again, and as you see, we get new updates. So I'm basically running out of time, but this was it already. So let me go just back to the slides for one final important thing, which is to thank all of you for coming and to maybe you find the time to feed the monkey. So not me, but the survey monkey up there. So this not only helps me to improve, but also to make the whole event better for the organizers. Since I'm basically over time a bit, sorry about that. I think it's not possible to take questions now, but I stick around, of course, for the whole day. Just find me, and I'm happy to discuss anything you want to know. Thanks a lot for your attention and being here.